Today's class I want to start a slightly different topic called network flows. We did discuss in the last class that we will spend some time in this class on the problem set that I gave out to the students. So we shall do that towards the end. So as soon as I finish with network flows, which should take me about 70 or 80 minutes, then we can spend the last half an hour to 40 minutes on doing the problems that I gave you out, gave out in the problem set, as well as to answer any questions that you might have on topics that I have taken up through these 3 days, as well as any other topics you might have in the area of data structures and algorithms. So first I want to do the network flow part of it, so that while we are still fresh in our minds and so on, we can go through the theory of network flows. Okay, so just a quick summary of where we are. I started by telling you where the whole area of graphs fits into the data structures and algorithms, and I said basically that graphs give rise to some number of prototype problems. We discussed already a few problems like shortest path problem. We discussed the coloring problem. We discussed we're going to discuss today network flow, and we saw basically that these prototype problems can be modeled in the form of graphs, and then you can apply algorithmic techniques like greedy algorithm. Yesterday we discussed, on Tuesday we discussed how to use the greedy algorithm. It's called Dijkstra's algorithm to do the shortest path problem, and we can do dynamic programming type methods. Dynamic programming is dividing a problem into sub problems and then solving the sub problems and then finding solution for the problem from the sub problem solutions, and that if you do systematically, it turns out to be a very powerful technique, right? So we discussed the Bellman-Ford algorithm, right, in the last class, and today I will be talking about yet another algorithmic method which is called network flow. And then we saw that for doing any of these algorithmic methods, you could use a variety of data structures. In fact, we were seeing arrays and lists, adjacency matrix, adjacency list, but stacks and queues. If you're doing breadth first search, you use queues. If you're using depth first search, you use recursion, which is essentially using stacks. And then we also saw that you can improve Dijkstra's algorithm by using the heap data structure, right, which is a priority queue data structure, as it's also called. And typically in graphs, the algorithm analysis is in terms of number of nodes and number of edges, that is in terms of n and m. Then we talked about various kinds of things in graphs like paths and how to represent graphs using adjacency matrices and so on. We talked about traversal, breadth and depth first traversal, which I hope by now you have a good hang of, right? Because we did some problems and so on. You have a good understanding now of these two techniques, traversal technique, breadth first search and depth first search traversal technique, right? You have a good understanding. And the more you practice it, all these algorithm methods theory that is sitting in class is only 10 or 20% of your learning. 80% of your learning will come when you actually apply these in terms of trying to do programming. So I strongly encourage that all the algorithms that we are discussing in class, like for example the problems that I gave you, find a cut vertex in a graph and so on, try to write program with it, right? Try to program it using your favorite language. It could be Python, it could be C, it could be C++, doesn't matter. Take your favorite programming language and try to write a simple program which will read a graph and find a cut vertex, for example, right? And that's how you learn. You will learn 80% from programming and you learn 20% by listening to what I'm saying in class. So programming is the only way to really learn all this algorithm stuff. So I encourage you strongly to actually program. In fact, a typical data structures and algorithms course that we run here in IIT, more than 50% of the weightage, the marks that we give is for programming. And even the NSEM exam that I run typically has online programming assignment. Okay, so we have a lot of programming. So programming is how you learn all these things. So I encourage you very strongly to try programming, because also it will help you when you go for job interviews and so on. These are the things that people test. They test whether you have good skills in programming, these kinds of algorithms. Okay, so we then discussed single source shortest paths, and we talked about two methods, the greedy method and the dynamic programming method for it. And then I also talked about minimum spanning tree, which is not about shortest path, but it's about finding how the shortest way of connecting a bunch of points. So instead of paths, we are looking at trees. So you can do shortest path, or you can do shortest or smallest or minimum spanning trees. Okay, so this is the various things that we have discussed so far. So that basically gives us the context now to discuss completely new method of doing things, which is called network flow. Okay, so in order to introduce network flow, I am going to introduce yet another concept. So far, what we have done is we have taken graphs and we label the nodes. So we mark the nodes as visited. We gave certain counters to the nodes, pre counter, post counter, right, low counter, and so on. We gave some counter values to the node, and then we took graph with edges which are weighted. We gave weights to the edges. Typically, we think about weights in terms of cost. So what does it cost to connect one node to the next node, for example? How much money I have to spend to go from here to there? This kind of thing. Okay. But today I am going to think about this weight not as a cost, but I am going to think about the weight of the edge as something else which is called capacity, right? Capacity. So that's how network flow, in some sense, algorithms are different from the traditional algorithms that you will see in graphs. They are thinking about the edge weights as representing something called capacity of the edge. So what is capacity? Capacity means how much of, we'll discuss what flow is, how much of flow can be put through the edge. Imagine that this node is representing like a town or something like that, and the edge is representing a road. We are asking how much traffic can be put through this road, how many cars in a day can be put on this road between these two cities, for example. So then it will represent capacity. Or for example, nodes could represent points on a river, and the edges could represent the amount of flow, actual water that can flow through a canal between these 2 points. Then we can ask, if I know between 2 edges this much of water can flow, then between 2 cities that are connected in multiple ways via a number of canals, how much water can flow between these 2 cities? This kind of question I can ask. Okay, so we are thinking about the edge weight now as a capacity. So we write, instead of writing W of E, we write C of E. Okay, C of E, which means capacity of the edge is C of E. Okay, so once we have uh, written capacities for all the edges, then we can look at flows through the graph. But typically, when we look at flows, you think about a flow from a source node or a source vertex to a sink node, which is represented by T. The source vertex is designated as S, and the sink vertex is designated as T. So typically, when we look at flows, we want a graph in which the edges, it's a directed graph, the edges are weighted by what are called capacities, and the source, there is a specific node which is basically designated as the source, and there is another node which is designated as the target. Okay, so the source node is called written as S, the target node is written as T, and when you say that a node is a source node, basically what you are saying is that the source node has no incoming edges, right? There are no edges coming into the source node. Similarly, the target node T is a node where there is no outgoing edges. So nodes uh, which have both incoming and outgoing edges are called internal nodes. Okay, so there are 3 kinds of nodes. There is a single designated node called a source node with no incoming edges. There is a single node called the target node with no outgoing edges, and then the remaining vertices are called internal vertices of the graph. So let me show you an example of the kind of graph we are looking at. So here is an example on which we can start looking at flows. So you can see here this graph has 4 vertices. One vertex has been designated as S. This vertex has no incoming edges. So this is the source vertex. This node over here is designated as T. It's called the target or sink vertex, and it has no outgoing edges. And there are 2 internal vertices in this graph, and you can see the capacities have been written on all the edges. Okay, so this is the kind of graph on which we want to model the flow problem. Okay, so quickly we can move on to the definition of a flow. An ST flow, right, means flow from S to T. S is the source, T is the target. ST flow is a flow from S to T, is a function f on edges. Okay, it's a function f on edges. So you're associating with each edge a real number. Okay, and the real number has to be positive. Now I told you in the previous thing that there are capacities. Now these capacities are expected to be positive. Okay, they are all positive capacity. So the flow also likewise is positive. So the flow is a number that you associate with every edge, which is a real number, and this number is expected to be positive. That's why e to r plus. Okay, and the flow satisfies two conditions. The first condition it satisfies is what is called the capacity condition of the flow. Okay, the capacity condition of the flow says that at no time the flow that is assigned to an edge can increase the capacity of the edge, which means the edge has a certain capacity to carry flow. The amount of water that a canal can carry, you should not put more water in the canal than what that canal can carry, right. So the flow that can be carried by an edge is bounded by, is less than equal to the capacity of the edge, and the flow is positive, right. So it means it's greater than equal to 0. So 0 less than equal to Fe less than equal to C. This is called the capacity condition. The second condition that the flow satisfies is what is called the conservation condition. If a canal flows into some point and carries water, there is no way for the water to stay there, it has to go out. So the amount of water taken out from a point is equal to the amount of water flowing into a point, similar to a current, right. If I have a node in a circuit, right, the amount of current flowing into the node must be equal to the amount of current flowing out of the node, Kirchhoff's law, as we know, right, Kirchhoff's current law. So this is written like this: for every vertex V, every internal vertex V, right, the amount of flow into that vertex, how is it calculated? Take each edge that is incoming edge into that vertex and add the flow of that edge. Okay, so if you keep adding all the flows of all the edges that are incoming into that vertex, you get the incoming flow for that particular vertex. Similarly, you can calculate the outgoing flow for that vertex, sigma E out of V, F of E. These two should be equal. Amount of flow going into a vertex should be the amount of flow going out of the vertex. No flow can stay at a vertex, or no new flow can be created at a vertex. That is what this is saying. So any function f that gives a value to every edge in such a way that it satisfies the capacity condition and the conservation condition is called a flow, right. So in particular a very trivial flow assigns to every edge the value 0, okay, the value 0. When I said positive, it can be 0, right, can be 0 also. So I can assign to every edge the value 0, and that will be a flow where it satisfies the capacity condition because it's greater than equal to 0 and it's less than equal to CE, and it satisfies the conservation condition because incoming is 0, outgoing is also 0. So in particular, assigning f equal to 0 for all edges is a flow, right. So we can start with that as a flow, and then we can build a bigger flow from it. So here is an example of a flow on this graph, right. So if you take this graph, I have associated with each of the edges here a number. How did I write it? The second number, that is A slash B, right. The second number B is the capacity of the edge. The first number here is the flow. So out of 20 capacity, I am putting 20 in this edge as the flow. On this edge, I have 10 as the capacity, I put 5 as the flow. On this edge, 30 is the capacity, 15 is the flow, 10 is the capacity, 5 is the flow, 20 is the capacity, 20 is the flow. So we are seeing basically at all edges, right, on all edges, I have not exceeded the capacity of the edge. It's at most the capacity of the edge. Therefore, the capacity condition is satisfied, right. So for this edge, for example, the flow is 5, capacity is 10, so it is satisfied. Like that for all edges, the capacity condition is satisfied. I can also check very easily that the conservation condition is satisfied. Take this node for example, the total flow coming into this node is 20, right, flow coming in is 20, flow going out is 15 on this edge, 5 on this edge, so there is 20. So 20 is coming in, 20 is going out, therefore conservation is satisfied for this node. Check for this node, 5 is coming in, 15 is coming in, 20 is going out, 20 is coming in, 20 is going out, therefore conservation condition is satisfied for this node. Okay, so all internal nodes, obviously conservation condition, it does not make sense for S because there are no incoming edges for S. So when we write conservation condition, we write it only for all the internal nodes. I didn't write it, I didn't say it here, but you should write it only for internal nodes. Okay, conservation condition is only for the internal nodes. So the S and T are, S is sourcing the flow, T is sinking the flow, and all the internal vertices are just passing the flow. They are taking input flow and putting it on the output. Okay, they are just passing the flow. Okay. So this is in an electrical circuit, this is obvious, right? The source can be a battery. Battery is the only thing that can source current. All right. The T can be the earth, which can the only thing which sinks current in typical electrical circuits. And all your internal nodes conserve current, which means current comes into the node is equal to current going out of the node. So it's like that. So the value of a flow Vf, value of flow Vf is simply defined as the total flow going out of the source vertex. So E out of S, S is the source vertex, E out of S, F of E. So the total flow out of the source vertex is called the value of the flow, right? F. So in particular, if you take the simple flow where F is equal to 0 for all the edges, the value of the flow will be 0, okay? So I can simple notation I am going to use when I write F out V. When I write F out V, what it means basically is the total flow that is going out of the node V. So the total flow going out of the node V, E out of V sigma of that is called F out of V. Similarly, F in of V is the total flow going into a node V. Okay, so E into V, Fe is called F in V. So the conservation condition can simply be said as for all internal nodes V, F in V must be equal to F out V. Okay, just the simplification. So I don't have to keep writing sigma E into and sigma E out and all that. That's why we are writing this. You can extend this F in and F out to sets. Okay, so if S is a subset of vertices, S is a set of vertices, then I can write F out of S is the total flow out of the set S. So there will be some flow that will be getting into S, there will be some flow going out of S, and there will be some flow rotating around inside S. We are not interested in the flow going around inside S. We are looking at the flow that is coming into S, which is called F in S, right? We are looking at the flow that is going out of S, which is called F out of S, and some flow which is inside S doesn't concern us. Okay, so for every set S, we can define similarly F out and F in of the entire set S. Okay, so conservation condition, as I said, we can write it as F in V equal to F out V, and the value of the flow Vf is simply F out of S, isn't it? It's the sum of the total flow going out of the source, V out, F out of S. Now, because the conservation condition is satisfied, therefore, it is very clear that whatever flow is coming out of S will be carried by all the internal nodes and eventually taken to the sink node. There is no other place for the flow to go. It has to go to the sink node. The drain, imagine in the house. The source is the tank, overhead water tank in the house. The water tank is giving water, it will go into all the rooms in the house, and then eventually it goes into the drain. Okay, so there is only one place for it to go, the sink. So therefore, all the water that is coming from the tank, wherever it goes, whichever room it goes, finally it has to go into the drain. So therefore, Vf, which is the total value of the flow, must be equal to the F out of S, must be also equal to the F in of T. Is that clear? So Vf, which is the value of the flow, is equal to F out of S is equal to F in of T, and all the other internal nodes are simply carrying the flow, right, through the node. All right. So let's consider this particular flow that I drew earlier for this graph. We can ask ourselves, what is the value of this flow? Now the value of this flow basically is the sum of the flow coming out of S. So 20 is going in this direction, 5 is going in this direction. So the total flow coming out of S is 25. So therefore the value of this flow is 25. And you can check basically that the total flow going into T is also 25. 5 is coming like this, 20 is going like this, 25 is going into T. Okay. So V out of S is equal to V in of T is equal to the flow, value of the flow, Vf. In this case it's 25. Okay, so the question that we are asking, or the problem that we are trying to solve, or the problem that we are trying to address here, is called the maximum flow problem. So given a directed graph with edges on whom we have placed capacities, alright, and given that the graph has a source node, source vertex and a target vertex, a sink vertex, we want to find a flow F, right, which has the maximum value, which means maximum value of Vf. Vf is maximum for the flow. So which flow will maximize Vf? This is the question we are asking, and this problem is called the maximum flow problem. Okay, it's called the maximum flow problem, max flow problem. Now a very important theorem which hope as we go through this lecture, we will get to see the proof of it in a sense also, is that the value of the maximum flow is equal to also the size of or the capacity of the minimum cut of the graph. Okay, it's a very important theorem in graph. Okay, that max flow is equal to min cut. So in order to understand that, we have to understand what is the min cut. What is the cut first of all? The cut is a way to cut the graph into two parts. We already discussed this, right? We can cut the graph into two parts. We talked about bipartite graph, for example. We can cut the vertices into two halves so that in each there is no edge inside V1, no edge inside V2, and all the edges are between V1 V2. That's a bipartite graph. We talked about other ways of cutting. But anyway, here we are not talking about bipartite. We are saying, can I draw a line through the edges like this? Draw a line. Here I have drawn the dotted line, right? It cuts some of the edges. So you can see that some nodes fall to one side of this edge, some nodes fall to the right side of this line. So we should draw a cut in such a way that S should belong to one side and T should belong to the other side. Okay, you should draw a cut in the graph such a way that S is on one side of the line, T is on the other side of the line. So in this case, these two nodes are on one side, these two nodes are S is on one side, T is on the other side. Then you can ask how much of the capacity is this line cutting. Now when you say how much of this capacity this line is cutting, you have to look at edges going out from A to B. Okay, this is A. This set is called A. The set which contains the source S is called A. The thing which contains T is called B. Okay, so we are asking how many edges go across the cut line from A to B, and for those edges that are going from A to B, what is the total capacity? So you can see here in this case, this cut cuts three edges. This edge, this edge, this edge, and all of them are going from A to B. All these edges are going from A to B, and the total value of the capacity of these is 50. 10 plus 30 plus 10, 50. Okay, so this is a cut with capacity 50. Now I can draw another cut line. Here is another cut line. Okay, I have drawn it like this. Now to calculate the capacity of this cut, right? You see that this is now which is A. These two nodes are A because it contains this is the set. This is the cut which this is the part of the cut which contains A, S, and this is the part of the cut which contains C. So this is called B. Okay, so arrows which are going from A to B, you have to see. So this arrow is going from A to B. Is this arrow going from A to B? No, right? It's going from B to A, this arrow. So we ignore it. Okay, we ignore it. We are in calculating the capacity of a cut, you take only edges that are going from A to B. A being the thing which contains S, B being the thing which contains T. You take only arrows going from A to B. This arrow is going from A to B. So in this cut, the capacity of this cut is 20 plus 20, which is 40. Is it okay? So we got the capacity of this cut as 40. So you saw previously we got a cut with had capacity, you know, in the previous one we saw capacity 50 cut. Here we are seeing a capacity 40 cut. Can we find a smaller cut? Yes, obviously we can find a smaller cut. Imagine this cut, right? This cut like this. This cut has two edges going from A to B. This A has three nodes, B has only one node. This is a cut, and this cut has capacity 30. I could also consider a cut which cuts these two edges, right? I can make a cut like this, that also will have capacity 30. So very easily by examination of this graph, we can see that among all the cuts of the graph which separates S from T, right, the minimum capacity cut is 30, isn't it? The capacity of the minimum cut is 30. Is it okay? So which means by if the max flow min cut theorem were true, and we are going to prove it, which means that the maximum flow you can put through this graph is 30. But clearly in some sense it's obvious that the maximum flow you can put through this graph is 30, because you can see that only 30 is possible from S. This node has capacity, this edge has capacity 20, this edge has capacity 10. So there is no way you can get a flow which is more than 30 from S anyway, isn't it? So it's quite obvious that the maximum flow will be 30 in this graph, but it's not so obvious in other graphs. You can have a very large graph where the min cut may be, for example, 15, and the flow going possible from S might be 30, but the min cut might actually be 15. So the max flow min cut theorem will tell us basically that the best flow you can put through this graph is 30 because the min cut is 30. Okay. Now the algorithm that we are going to discuss to find the maximum flow, right, is called the Ford-Fulkerson algorithm after these two people who invented it. okay, and it's again an algorithm 1956. So you can see that many of these very fundamental, very interesting algorithms in graphs especially, were all invented before big computers were there actually, right? Before we had very large computers, right? The interesting computers all came in 1960s. 60s we did not have any big computers, okay? The big computers started coming in 1960s, right? And so we can see that many of these new beautiful algorithms were discovered even before the advent of real computers, all right, that as we know of them today. And so these guys actually did their algorithms by hand, programs by hand. So this Ford-Fulkerson algorithm, it finds the maximum flow in a graph, and therefore from that maximum flow you can also find the, okay. Now just like we did earlier, before we start discussing a new algorithm, we are going to try an existing algorithm first, okay. We are not going to just jump into the new algorithm. We'll try an existing algorithm first, we'll find out why that algorithm does not work, and then we'll try and see if we can improvise, right, to make a new algorithm. Always you should do that. If you find a problem, try to see whether or not your existing method works. Don't start trying some new method altogether new method. And the last thing you should do is try brute force, okay, that doesn't make sense. You see whether you can model the problem and see whether you can attack it with these known methods like divide and conquer, greedy, dynamic programming, these kind of methods. And if you can't do these methods, then you try and see whether you need to find a new method, improvise, okay. So I am going to see whether I can do greedy on this first, right. So how am I going to do greedy? I am going to say, okay, the flow is going to be consisting of paths, right. Eventually all flows will be a collection of paths, because water, for example, in a river, it flows along a straight line, we know that. So we'll try and take paths and we'll add up paths, and then we'll try to make the flow using the sum of paths. Is that okay? That makes sense. So let's start with one path. So in this case, I'm starting with the path SUVT. Okay, I can start any path, but there is no path going like this. I could have started with the path SVT, or I could have taken the path SUT, but I just decided that I'm going to take the path SUVT. Okay, can take any path, doesn't matter. So let's say I took SUVT as the path. I'm asking, the first question I have to ask is, in this path, what is the maximum flow I can put? Okay, so for a path, it's very clear that the maximum flow I can put in a path, right? Maximum flow I can put in a path. So in this case, this edge is capacity 20, this edge has capacity 30, this edge has capacity 20. So the flow can't exceed the capacity of any other edges, isn't it? So therefore, I cannot put more than 20, because 20 is the least capacity edge on the path, right? So if I have a path, then it's easy to calculate the maximum flow I can put in that path by just finding the least capacity edge on the path. Take the capacity of all the edges, find the minimum, that should be the bottleneck as it's called for this path, and that will give you the maximum flow that I can put on this path. So in this case it's 20. So I can put 20 on this edge, 20 on this flow, and let's say I put 20. So I put 20 on this, I put 20 on this, I put 20 on this, okay, and I put on the, to make a flow I have to put something on every edge. Okay, to make a flow I can't just take one path and do what I want with it. I should put a flow is defined as a value that is associated with every edge of the graph. So I put something on these two edges. So I'm putting 0 because no flow on those edges, right? So 0. So this is defining a flow on this graph where I put 20, 20, 20 on these three edges and 0 on these edges. Okay, this is a flow, right? Now this is a flow, and in fact I found a flow of size 20. Remember the min cut for this was 30. So if I believe that max flow is equal to min cut, then I know that maximum flow in this graph is 30. I have now found a flow of 20 using this path. Now can I somehow increase this flow from 20 to 30? This is the question I'm asking. By adding another path to it or something. Can I increase it? But the problem we have now is that we are stuck. We are stuck. Why are we stuck? I really can't add any more flow. Now in this direction I can't add a flow because this edge is already capacity, right? This got 20 capacity, I am putting 20 flow, is nothing further I can put. I can only put more flow on this direction if I want. So let's say I try to put some flow on this direction. I can't push on this. So I push the flow on this direction. Okay, I push the flow in this direction. How much flow I push? Let's say I push a flow of x. I want to push 10 ideally, but let's say I push x. Okay, some x which is less than equal to 10. I push on it. Now this flow will come to V. From V, it can take two ways. You can try to go like this or like this. If I try to go like this, I can't. Why can't I go like this? I can't go like this because the edge here is pointing like this, downward. So there is no edge pointing from V to U. So there is no way to take a flow in this direction. We will see shortly that we will do some interesting trick to make the flow go up actually. Okay. But right now we can't make the flow go up because there is no edge there. There is no edge there, so there is no way to make the flow go up there. So the only way to take the flow is in this direction, isn't it? So I try to take the flow in this direction. So if I take the flow in this direction, then this x will get added to 20 and I get a total flow on this edge is 20 plus x. But what has happened, if x is positive, 20 plus x is greater than 20. And therefore what has happened to this edge? We exceeded the capacity condition for this edge. So what does it mean? It means that once I have pushed 20, 20, 20 like this, I can't push any more flow through this graph. We are finished, okay, we are stuck. There is nothing I can do because any additional flow that I do has to start like this. I can't push it like this because it's downward directed. I can't push it like this because this is capacity exhausted. Okay, so my first thought is that can I modify my original flow somehow? Can I add the original flow which I pushed? I was greedy, right? I was greedy. What did I do? I took maximum flow of this path, which was 20. I didn't have taken 20. I could have taken something less. So I am asking the question, can I adjust the first flow? Can I reduce the first flow a little bit so that I can accommodate x on this direction? Right. So I have to reduce this by x in order to accommodate x. So let me try and reduce the first flow by x. So I reduce this by 20 by x, this by x, this by x. So the entire first path I reduced by x. Because I reduced it by x, I can now add x on this path. So I can have a flow of x which goes like this, now because I reduced this by x. Okay. But what is the total value of this flow? It's 20 minus x plus x back to 20, isn't it? So I have reduced the first one by x, I added x, total flow value is still 20, but now I have an interesting flow where part of the flow is going like this and part of the flow is going like this. Except that it's interesting, but the value of the flow is still 20. Okay. Now obviously if I want to choose some value for x, I will choose 10 because there is no reason to choose anything less than x, 10. So let's say I choose 10. So I have x is equal to 10, which means that 10 value of flow is going like this. On this edge is saturated now, 20 minus 10 plus 10 is equal to 20 is saturated. On this edge now I am carrying 10, on this edge now I am carrying 10, and then this edge I am carrying 0. Now I ask the question, given that I have modified the first flow by reducing it by 10 and pushed the second flow like this, can I now add something to this flow? And the answer is yes, I can, because since this edge has only 10 now, I can push another 10 flow like this. That 10 flow can go like this or can go like this because both these edges have additional capacity. It can go 10 like this or it can go 10 like this. But if I set that flow 10 like this, it will not be able to go any further because this edge is saturated, isn't it? So if I push 10 like this, the only way to take it out of this node is to go like this. So I can push a 10 flow like this, which will go like this, and I can get an additional 10 flow. Okay. So now that I have got this, I can add a flow, another flow of 10 like this, which goes like this, and that will give me a flow which looks like this now. So what is the maximum value? What is the value of this flow? 10 plus 20, 30 is the value of this flow. So in this flow, 10 is going from here, 10 is going like this, and 10 is going like this in some sense. 3 paths. Okay, one path like this carrying 10, one path like this carrying 10, and one path like this carrying 10. Sum of those 3 paths is 30. Is that okay? So this is how I constructed this flow. So we can see basically that this flow, this new flow which I have constructed by starting with the first greedy path which I created, then adjusting the greedy path to accommodate a flow from here, and then putting the last flow gives you the equivalent of the maximum flow, which is equal to the minimum cutoffs. Okay. So I want to formalize this method, whatever I did now. I did something, right? I did something I did. I started with some greedy flow, I modified it, and then I kind of pushed another flow and I did all that. I want to formalize this algorithm. So in order to formalize it, I am going to define something called a residual graph of a graph. Okay. Now basically what I want to do is, you can see here what I did here when I did this reduction, right? When I did this reduction, what did I do here is I did undo operation. I had a path in which I had pushed 20 flow. I want to undo part of that flow. I don't want to push 20. I want to reduce it. So I'm undoing. Okay, I'm doing undo operation. So what I want to do basically is I want in my algorithm a method to undo a flow. I want to undo. Okay, because that way I can push additional flows because I undo a flow. Right. So the residual graph in some sense models the balance capacity. After I put a flow through a graph, what is the balance capacity that's available and how much I can undo. Can I undo? If I undo, what how much I can undo. So these are the two things it models. So given a graph G, I can construct a new graph which is called the residual graph GF. Okay, why am I writing GF? Because the residual graph G is defined with respect to a flow F. Given a graph G and a flow F on that graph, I can create a residue, a balance graph. After this flow has been taken out, what is left in this graph is what I am asking. That's the residue. Plus, if I can also undo the flow. So how much can I undo of the flow and what is left after the flow is going through the graph. These are the two things that the residual graph is carrying. Okay. Now clearly this undo operation has to be modeled using some kind of edges and the balance what is left has to be modeled by some kind of edges. So I need two kinds of edges in the graph. Okay. So the edges which are the balance edges are called forward edges and the undo edges are called the backward edges. You will see with example, right? You will get to understand with example. Forward edges and backward edges. For each edge in the graph, right? Each edge in the graph, wherever FE is less than CE. Clearly, if I put a flow through an edge, that flow has to be less than equal to CE, right? But we could have a situation where FE is less than CE, or you could have a situation where FE equal to CE. If FE is equal to CE, that edge is called saturated. FE equal to CE. So if I edge had capacity 20 and I put a flow of 20, that edge is saturated. For saturated edges, there is no residue, there is no balance capacity left. Okay, so the residual graph carries no edge. Wherever there is a edge where FE is strictly less than CE, then what has happened is that I am not using up the full capacity of the edge. So the balance capacity CE minus FE is what I am going to write as the residual capacity of that edge in the residual graph. Okay. So whenever FE equal to CE, I drop that edge. Whenever FE is less than CE, I keep the edge and I write on that edge not CE but I write CE minus FE, which is the balance capacity of the edge. Such edges are called forward edges of the residual graph here. Now similarly, for every edge E equal to UV in the graph where the flow is non-zero, which means there is some flow, right? If it is zero, there is nothing I can undo. Wherever the flow is non-zero, I can undo that FE, right? That FE value can be undone. Just like we saw last time we had 20, I could undo some part of it. I could undo 10, right? I could undo all of the 20 also. So I can undo up to FE, which is why what we do is we write an undo edge, right, or a backward edge in the graph GF and put on that backward edge a capacity which is equal to F of E, which is the amount by which you can undo. So let me just show you for this graph that we took and this flow F that we took, what does the residual graph look like? Firstly, you have to start with the residual graph having nodes which are the same as the original graph. The SUVT were the original nodes, the SUVT will be the same nodes in the residual graph. Second, what you will do is for every edge that is there in this which has a flow which is not equal to capacity. So this one has a flow which is equal to capacity. Here you have an edge which has a flow which is less than capacity. Here you have an edge which is less than capacity. Here is less than capacity. So these three edges have less than capacity. For these kinds of edges, you want to put an edge in the residual graph. And what weight you should put on that edge? You should put a weight which is equal to the balance residue. Okay. So since this was 0 here, balance is 10, 10 minus 0. So that's what you write here. Here you put 20, so 30 minus 20, 10. That's why you put 10 here. Here it was 0 out of 10, so 10 minus 0, 10. Here there is no balance capacity, so no edge. Here also no. These are two saturated edges, which is why you are not putting any edge in the. So you first construct these forward edges by looking at those edges where there is some balance capacity and you put. Okay. The second is you want to put edges which are undo edges, undo, backward edges, undo edges. Okay. Which are the ones you can undo? I can undo this because this is carrying flow of 20. I can undo this, I can undo this. There are 3 undo edges. So I want to put 3 edges called backward edges in the opposite direction, where I am undoing in the opposite direction, right? The flow was going like this. The 20 that you put was like this. If you want to undo, I have to do it this direction. So I can undo the flow by putting a flow, reverse flow of size 20 like this. So basically imagine that the 20 went like this, 20 went back like this, right? So that means that you undo that 20, completely undid that 20. Okay? That's why I put this undo edge of 20. And here there was a flow of size 20, so I can undo up to 20. That's why I put a edge of capacity 20 in this direction. And similarly there was a flow of 20 like this, so I can undo that 20, so I put an edge of size 20 in this direction. So there are 3 dotted edges or backward edges or undo edges of capacity which is equal to the capacity of the flow. Okay. Now that I have created this interesting graph called the residual graph, I can ask the question, is there a path in this residual graph from S to T? Obviously there is a path. I can go like this. I can't go this way because there is no edge like this, but I can go now on this undo edge. This is the undo edge. I can go like this, go on this undo edge and go like this. So there is a path from S to T. So I can ask the question, is there a path in this ST path in this residual graph? If there is, what is the path and what is the maximum flow I can put on that path? So let's say this is the path that I can take in this residual graph like this. This path, what is the maximum flow I can put? The maximum flow I can put on that graph, on that path, is the minimum weight edge on that path, isn't it? For any path, the maximum flow is equal to the minimum weight edge, because remember the flow on the path has to not exceed the weight of any of the edges on the path. Therefore, the minimum edge weight will be the maximum flow. So 10 is the minimum edge weight. Therefore, the biggest flow I can put through this is 10. So I put a flow of 10 in it. Okay, so if I push 10 through this, then I can write a new residual graph. Can I construct a new residual graph? How do I construct a new residual graph? Take this graph, take these flows, this new flow that I have. In fact, actually I am taking the old flow and the new flow, adding the 2 flows. So I get a big flow, and then with respect to that flow I am constructing the residual graph. Okay, but I can also do it on this graph directly. So I can make a residual graph, right? So how do I make the residual graph? So since this edge now is saturated, in the residual graph now there is no edge. Since this edge is saturated, in the residual graph there is no edge. Is that okay? Now this edge had a capacity of 20, this dotted undo edge had a capacity of 20, I used up 10, so I am left with 10. Okay, what it's saying basically is that I could undo up to 20, but I have undone only 20, so I can undo another 10 more. What it's saying, that's all it's saying. Okay, this edge I have not used at all, so it's still there. This edge I have not used at all, so it's still there. So from this graph I can construct the residual graph again, and this gives me the residual graph. Now I can ask, in this residual graph, is there a path from S to T? The answer is there is no path from S to T, because only one edge is there, and that is an inward edge into S. So no path from S. Since there is no path from S to T in this graph, algorithm stops. Okay, algorithm stops, no path. And then we have constructed 2 flows, one of size 20, another of size 10. You add it up, you get a flow of size 30. You got a maximum flow. Okay, now of course I'm going to show it to you. I'm going to prove that all this works. Okay, so just be patient and you'll see the proofs. Now note firstly that the residual graph can have at most twice the number of edges as the original graph, because for every edge in the original graph, either I removed that edge if it was saturated, or I kept the edge if it was not saturated, and I added a dotted edge in the opposite direction. Okay, so at most every edge will get an additional dotted edge, so we will get twice the number of edges as was there in the original graph. So in some sense the order of number of edges, if m were the number of edges in the original graph, the number of edges in the residual graph is also order m. So working with the graph or working with the residual graph does not change the complexity of the problem in terms of order, okay, because the number of edges is only increased by constant number of edges, twice. Okay, now I am going to present Ford-Fulkerson algorithm, but because we don't want to keep constructing in some sense multiple residual graphs. We're going to do all this with the original graph and by augmenting the flow, by looking at the flows. So we'll use the residual graph, but we'll use it to construct flows. So we're going to discuss something called flow augmentation. Given a flow F, can I augment this flow? Can I add more to this flow and make it another flow, F1 to F2 to F3, where F2 is greater than F1, F3 is greater than F2 and so on. Keep on increasing the flow. Okay. Can I keep augmenting the flow? Is the question I'm asking. And in order to augment the flow, we are going to use this residual graph concept. So let B be a simple path from S to T in GF, right? GF, remember, is the residual graph obtained. I have a graph G, I add a flow F, I made the residual graph GF, and then I looked at whether there is a path from S to T in this GF. And suppose there was a path P, then P basically can be used to augment the flow F, isn't it? I can add to the flow F by using P. So I'm asking, what is the augmented value of the flow using this path P? In order to define the augmented value of the flow, first I need to see what is the maximum value of flow I can put through the path. So bottleneck PF is basically defined as the minimum residual capacity of the edges on the path P. Okay. After you have put the flow F through the graph, what is the residual capacity left? Bottleneck PF basically gives you the minimum of that. So that basically gives you, right? I mean, we'll see an example, so you'll get to know what it is, right? So bottleneck is the minimum in the residual graph GF. The least value of the weight of an edge basically is bottleneck PF. So augment FP, which means augment the flow F by using the path P, is a new flow obtained by augmenting F by using the path P. How do I augment the flow? First find out what is the bottleneck of the path P. Let it be B. For bottleneck means the least weight edge on the path P. For each edge E equal to UV on the path P, if E is a forward edge, then increase FE in G, the original graph, by B. Otherwise, decrease FE in G by B. Okay. Either add B to the flow, add B to the flow, or decrease B to from the flow, depending on whether it's a forward edge or a backward edge. Remember, a backward edge means undo, so you should decrease the flow. A forward edge basically means balance capacity is there, so you want to increase the flow. Okay. So you are basically checking what is the minimum weight edge on a path and using that bottleneck to increase or decrease the flow on the edges of the graph accordingly, right? So a path P in GF is called an augmenting path. Okay, any path in the residual graph is called an augmenting path because I can use it to augment the flow. And we want to show basically that if I augment the flow, right? So in this example, we had an initial flow F of size 20, right, which went like this. And this was the residual graph we constructed from that flow. And then we found a path. We say, let us find a path. So there is a path. This is the path. This path has 3 edges, 10, 20, 10 are the weights of those edges. The bottleneck of this path is 10. This is the least weight edge. Okay. So bottleneck B is equal to 10. So to augment this flow, what we are going to do basically is we are going to take 10, which is B, and we are going to say on this path, every edge which is a forward edge, add 10 to the flow. So in this flow, whatever flow I had here, I can add 10 over here, right? And similarly, this is a forward edge, so I can add 10 over here. So add 10 here, add 10 here. And what should I do to this? This is a backward edge. So since I have taken a backward edge and I took 10 here, what should I do to this edge? I should reduce 10 from this edge. Okay. So for every forward edge in the ST path in the residual graph, add 10 to the thing, and every backward edge subtract 10 because you are undoing, no? That's why. So here I want to subtract 10, so this becomes 10. So the new flow that I will get by augmenting this particular flow using this path, right, is equal to the existing flow modified like this. Add 10 to this edge, add 10 to this edge, subtract 10 from this edge. And the result will be you will have 20 here, 10 here, 10 here, 20 here and 10 here, which is the flow we got by doing all these tricks, right, in the end. The final flow which we got. is this, right? So that is the flow. Okay, so that is called augmentation of a flow using a path. So the first thing I want to show basically is that if I take a flow and I take a path and augment it, then what I am going to get is a flow, right? Taking a flow and augmenting it using a path from the residual graph will also result in a flow. In order to show that it results in a flow, I have to show two things. One, that it satisfies the capacity condition, and two, that it satisfies the conservation condition, right? Capacity condition means that none of the edges of the original graph, the capacity is exceeded because of augmentation. Second, I have to show basically conservation condition. I have not augmented the flow in such a way that there are any nodes where the incoming and outgoing flows are not equal. Okay, that has not happened. So I have to show this. So it's not difficult to show it. How to check capacity condition? I have changed the values of the edges, the flow on the edges by B, right, along the path P. So if you look at F prime E, we know basically that if it's a forward edge, then I've added B, right? So F prime E is equal to Fe plus B. So Fe plus B, since Fe is greater than or equal to 0, Fe plus B is also greater than or equal to 0. So that part of the capacity condition is satisfied. It's positive, we know that. Did it exceed the capacity? The answer is that I chose B such that B is less than or equal to Ce minus Fe. B bottleneck is always less than or equal to, because remember the residual graph, the capacity of the edge is Ce minus Fe. The residual graph, the capacity of the forward edge is Ce minus Fe, which means the bottleneck B will always be less than Ce minus Fe. Therefore, Fe plus B will be less than or equal to Fe plus E minus Fe, which is C. So I am not going to exceed the capacity of the edge of the graph. Similarly, for backward edges, I must make sure that I am not making the flow negative, because I am undoing, right? When I am undoing, I should not undo so much that it becomes negative, the flow. I must check that the capacity, that flow that I am getting is positive. How do I check it? I know basically that F prime E for a backward edge is less than Fe. Why is it? Because I am subtracting B from the flow. Therefore, F prime E is less than Fe, and Fe is less than Ce, so F prime E is also less than C. So that part of the capacity condition check is easy. I already started with a flow which is less than the capacity. I reduced it, it will be less than capacity, no problem. But I should not make it go negative. How do I ensure that it's not gone negative? F prime E is equal to Fe minus B, isn't it? F prime E is Fe minus B. I have reduced B from the flow. Now remember that we have chosen the bottleneck B such that it is the minimum of the weight edges, or minimum of the weight of all the edges on the capacities of the edges on the path. So therefore, for the backward edges, the capacity that we wrote on that backward edge was F of E. The capacity we wrote on the backward edge was F of E. So therefore, B will be less than F of E. Because B is less than or equal to F of E, minus B is going to be greater than or equal to minus F of E. Therefore, Fe minus FB is going to be greater than or equal to Fe minus Fe, which is 0. Therefore, F prime E will be not negative. Okay. So I have ensured basically that the new flow that I get by doing this augmentation is not negative and it's not exceeding the capacity, right? Now the second thing I have to check basically is that conservation condition is satisfied. Conservation condition means that for all the internal nodes, I must check that the inflow and the outflow for those nodes is exactly the same. How do I check it? There are 4 cases I have to check. First case is, for a given node, the incoming edge in the residual graph is positive forward edge, outgoing edge is forward edge. This is a path, right? I have modified the path. I have taken a path and modified the weights. There is a question? Alright. Okay, so the bottleneck is the least weight edge in a path. Okay, bottleneck is the least weight edge in a path. So, the way to think about a bottleneck is, if I have a flow, right? So maybe I use the board. So, we can put it on the board. So I have a source node, I have the target node, and I'm taking a path which is going like this through the graph, right? There's a path which is going like this. Some of these edges may be forward edges, some of them may be backward edges. Okay, so I'm taking a flow which goes like this. Now, this flow cannot exceed the capacity of all these edges. So let's say this one has capacity which is 20 this one has capacity which is 5 and this has capacity which is 10. So we are asking, imagine that there is a road which is there from here to here and it is going through these 2 points. So car has to travel like this and like this, and let's say this 20 represents the width of the road, right? So this is like a broad road, this is a slightly broad road. So this 200 feet road, this 100 feet road, this 50 feet road. So question is, where will the bottleneck come for me when I am driving from here to here? Obviously the bottleneck is going to come on the most narrow part of the travel, right? When the road becomes narrow, it will become. Similarly, if I have canal, I have broad canal, lot of water can be carried. This is narrow, so very little water can be carried, like that. So the bottleneck for this particular path is going to come from here, because it's the least weight edge on the path. Is that okay? So bottleneck basically is the least, it's the edge with the least weight on a given path. That's called the bottleneck. Is that clear? So what we are trying to do is we are saying we want to increase the flow by the maximum amount. So in this particular example, we are saying I want to increase the flow by 5. I can't increase it more than 5, but I want to increase the flow by 5, which is equal to the bottleneck, which is why we are augmenting the flow by B, which is the bottleneck. Up to B we want to do, beyond B we can't do, so we are doing up to B. Okay, so we have to check 4 conditions. The first condition is the path basically that is passing through a vertex, both the incoming and outgoing edges are forward edges. If that were the case, then I am adding in the original graph B to the weight of the flow. I am adding B to the flow for the in, and I am adding B to the flow for the out. So this will not change the conservation condition for this node, because I added additional B to this flow, that B is going out of this node. So B is coming in, additional B is coming in, additional B is going out. So flow conservation condition is satisfied. Second possible case is that the path passes through the vertex in such a way that the incoming edge is backward edge, which is an undo edge, and the outgoing edge is a undo edge, backward edge. Both of them are backward edges. In which case, right, what I am doing basically is subtracting B, because an undo, right? I am subtracting B from the flow, I am subtracting B from the flow, both for input. Then if I am subtracting from both these places B, then I can see that the conservation condition continues to be satisfied, because what's happening is that B has been reduced, but B has been reduced here also. So it's satisfied. So the third condition is where the incoming edge is forward, outgoing edge is backward. Alright. If this is the case, then what I have done is I have added B to this flow in this edge, but I have subtracted B from this edge, but this edge is like this, right, because undo edge. Therefore the original edge was actually like this. So I subtracted B here and added B here. So what has happened basically is that flow is not going through the node, but is getting diverted in some sense. So in fact earlier when I added more flow in this, so more flow is coming from this direction, less flow is coming from this direction, but the total flow that is coming into this node is plus B minus B, additional flow is 0. No additional flow into this node. So I don't have to worry about the other edges, because no additional flow. Okay. Similarly, if I have incoming B, which is a dotted edge, backward edge, outgoing B is solid edge, then basically I have subtracted B here, added B here, which means that they had more flow going in this direction, less going in this direction. So therefore the total outgoing flow is 0. Additional flow is 0. So these two are examples of diversion. Instead of sending the flow, right, instead of earlier the flow was going like this, instead of sending the flow like this, I am sending the flow like this. That's what it means. Okay, so diversion is taking place. So I can check therefore by simple logic, I can examine and I can convince myself that if I take an F and augment it with a path P in the residual graph, the new flow, the new thing that I will get is also a flow. It satisfies the capacity condition, it satisfies the conservation condition. And therefore since that is correct, I can now write my Ford-Fulkerson algorithm. See how simple the algorithm is. Again, it fits in one page. Okay, algorithms that don't fit in one page are bad algorithms. Okay, you will write programs which will not work, you will make mistakes. You should be able to write your program on one page so that you can see the whole thing, you can take the printout, you can stare at it, you can find out if you have made mistakes. Right? Always try to write your algorithm with subroutines, everything in such a way that it is sitting on one page, so you can stare at the algorithm for a long time and see whether you have made mistakes. So initially we start with flow equal to 0 for all the edges, Fe equal to 0 for all the edges. while there is an ST path in GF. So, you know, if you take the flow F equal to 0, then the residual graph GF is equal to the original graph G. That's clear, no? Residual graph GF will be exactly the same as the original graph. So GF is equal to G. So while there is the ST path in GF, which is the same as G initially, take P to be an ST path in GF, augment the flow which you have got F with the path P to get a new flow F prime. Increase the flow by using the path P to F prime. Set F to F prime, right? Just like you set X to X plus 1 or whatever it is a variable, set your flow F to F prime, set your graph GF to GF prime, which means update your graph GF to GF prime, and keep on doing this as long as you can keep finding ST paths in the residual graph. When you stop finding a residual path, in an augmenting path, you stop. The flow you will get at the end is the maximum flow. This is what Ford Purkazar says. So first thing you have to check whenever, very simple algorithm, okay, it looks almost trivial, it looks as if actually it's quite hard to believe that just by keeping on finding paths and adding flow you are getting the maximum flow in this graph. There is no way to get a better flow than that, okay, that is what you are saying, but it does work and we are going to show that it works, okay. First thing that we are going to check is, does this algorithm terminate? Because you can keep on finding augmenting paths and it can keep on going, it will never stop. Can that happen? The answer, it cannot happen. Why can't it happen? Because remember, we are in the residual graph, we are not keeping zero weight edges. All the edges there have some capacity which is positive, right? If the residual capacity is 0, we are not keeping the edge in the residual graph. So only things which are positive we are keeping there. So the bottleneck B, when you look at a path, augmenting path, the bottleneck B is the least weight edge of that path, that will be a positive number. So every step B will be positive number, and since B is a positive number, the flow is increasing by a positive number. VF is increasing by B, so it's a positive number. Each time we augment, we are increasing the flow VF by B, and B is positive. So the flow keeps increasing, that is the first step. Can it keep on increasing forever to infinity? The answer is it cannot. Why can't it keep increasing till infinity? Because the total value of the flow is bounded by the total capacity of all the edges going out of the source node. So if I add up all the capacities of the edges going out of the source node S, that gives me the total maximum flow that I can have. So let's call that capital C. So the maximum value of the flow is bounded by capital C. The algorithm, even though the total flow is bounded by capital C, even though the total flow is bounded by capital C, and the flow at each step is keeping on increasing by a positive number, you may still not terminate. It can go on forever. I still need something else to make sure that it terminates. What is that? Can anybody tell me the answer to that? Can the algorithm, which is the total capacity, the total flow is bounded by some number which is capital C, and at each I am keeping on increasing, the total number is bounded, but still it can go till infinity for infinite number of steps. Can that happen? When can that happen? Can anybody tell me the answer? When can that happen? I need one more condition to make sure that this thing terminates. Can I have a number which is keeping on increasing, right? And is bounded. It's bounded. Something is keeping on increasing. It's bounded, but it can go on infinite number of times. Is there a series that you can think about which you can keep on adding, but it will never cross a number? Can you think of anything like that? Right? Remember that I have not told you that these are the flow. The flow is a mapping from edges to real numbers. Remember that, okay? So that's the hint. So if I have real numbers, is it possible that I can keep increasing the flow? And we'll come to this, okay? What is how do you define the cuts and all that? We'll come to later on, okay? I'll explain that from the flow. But meanwhile, can you answer my question? Can anybody answer my question? Is it possible that if I have real numbers, I can keep increasing the flow by augmentation? The overall flow is bounded by a number which is C, and I can still do this infinite number of times. Can that happen? Is it possible? Anybody? Okay, in principle it's possible, because if you look at real numbers, this is possible, right? So in the beginning I might increase the flow by 1, then the second step I might increase the flow by half, which is a real number. Then in the third step I might increase the flow by 1 by 4, which is another real number. Okay, the fourth step I might increase the flow by 1 by 8 and so on. So what is 1 plus half plus 1 by 4 plus 1 by 8 plus 1 by 16 plus and all that? How much does that add up to? What is the sum of that series? 1 plus half plus 1 by 4 plus 1 by 8 plus 1 by 16 and so on, right? If I add up like that, what do I get? Okay, somebody has tried to say it's 2. Okay, that's good. Good answer, 2. So if I keep adding 1 plus half plus 1 by 4 plus 1 by 8 and so on, I'll get 2. And if the total value of capital C were say 10, then I might have actually an infinite number of iterations and I might never really stop. It might just go into perpetual loop. Okay. So one more condition I need, right, which is that somebody has said that it's because of reverse flow we might have to infinite loops, but we are not actually doing reverse flow, we are only undoing a flow. Okay, of course we are undoing, and we are undoing only part of the flow. So right, but if it were real numbers, then that can lead to infinite loops. So the important condition that I did not state, that I should state, is that all the capacities are integers. So when you have capacities which are integers, natural numbers, positive numbers, not real numbers, then fourth Fulkerson algorithm will terminate. Fourth Fulkerson algorithm may not terminate for real numbers unless I ensure that it terminates. Again, it's a little harder, but if they are numbers, then usually you can write capacities as numbers, right? You don't need to write real numbers there. So most of the problems that we deal with, you can always multiply, scale it up by something and make them all numbers. So whenever they are integers, positive integers, fourth Fulkerson algorithm will terminate. I can ask myself, what is the complexity of fourth Fulkerson algorithm? Okay, how many iterations will it do? The answer is, since every iteration increases by at least 1, because they are numbers, positive numbers, bottleneck therefore is going to be positive, therefore it's going to be minimum 1, and the flow is bounded by capital C, therefore the number of steps can be at most C. Each time it's increasing by 1, total value is C, therefore the number of steps can only be C maximum. And each iteration I am doing order m steps, because I am going to examine the number of edges, and each edge I am going to do some work. So in fact actually I am only going to do one path. So the path itself can be of size order m. Okay. So therefore in each step I am going to do an augmentation thing which is going to be of order m size. Therefore I am going to do C steps, and therefore the total complexity is order m. Now C itself may be very large, so MC may be very large. Okay, MC may be very large compared to M or L, but later on we'll see. In fact, immediately I will show you that I can make it much smaller by doing some tricks. So order MC is the complexity of this algorithm. Now in order to show you basically that this thing gives you the maximum value, and somebody asked how do I choose the thing in terms of cuts and so on. So you will see how I am going to choose the cut. Okay, what is the cut I am making? Every time I am augmenting the flow, I am actually constructing a cut, and I am making the maximum flow. Actually I have constructed a minimum cut. This is what I am going to show you. Okay. So what is the cut that I am creating every time I create a flow? That's the question I am asking. So let AB be an ST cut, then you can see basically that the value of the flow VF can be written as how much of the flow is going out of A and how much is going back into A. So the flow which is going out of A minus the flow which is going into the A must be the value of the flow, right, clearly. So out of A into A, if I subtract these two, that must be the total flow going across this line, and that must have originated at S, therefore that is equal to the value of the flow. So if AB is an ST cut, then I know that the value of the flow VF is equal to F out of A minus F in of A, and since the cut capacity is defined as F out of A, remember, to define the capacity of a cut you don't look at edges which are going backward, only forward edges you look at. So the capacity of the cut is F out of A. Since VF is equal to F out of A minus F in of A, VF must be less than equal to F out of A. Okay. So VF is less than equal to the capacity of the cut, which means basically any cut you take of the graph, any cut you take in the graph, the flow basically that you get, any flow that you have, the value of the flow will be always less than equal to the capacity of that cut, right. So for any cut, the value of the flow must be less than equal to the cut, means that basically the value of the flow must be less than equal to the minimum cut also. So the value of the flow is bounded by the minimum cut, okay, bounded by the minimum cut. It's less than equal to the any cut, therefore it's less than equal to the minimum of all those cuts, and therefore it's less than equal to the minimum cut. It's bounded from above by the minimum cut. Now when we do augmentation, we are keeping on increasing the flow. So we are starting with a flow which is 0, keeping on increasing the flow, but every one of these flows is going to be less than equal to the minimum cut. What we are going to show is that when Ford Fulkerson stops, it's going to reach that minimum cut. It can't cross the minimum cut, it's going to reach it, okay. And therefore we are also going to show that the maximum flow is equal to the minimum cut. We are going to find that minimum cut, and all of that we are going to do. Okay, how am I going to show that when Ford Fulkerson stops, it found the minimum cut? I look at the cut that I get in the graph at the end of Ford Fulkerson algorithm. What is the cut that I get at the end of the graph? Take the nodes A star, okay, define A star as the nodes in the graph that can be reached from F in the residual graph GF, okay. You have a flow F which is the maximum of your flow, which at you run Ford Fulkerson, it ended with a flow F. After doing all this augmentation, it ended with a flow called F. Make the residual graph GF. Remember that in this residual graph GF, there is no path from S to T. If there were paths from S to T, the algorithm wouldn't have stopped, it would have continued. Algorithm stopped, which means there is no further path in S from S to T in GF, okay. So this final GF which I got, there is no ST path. Since there is no ST path, it clearly somewhere S and T are disconnected in the GF graph, isn't it? They're disconnected. There is no path, it's disconnected. So I want to take all those nodes which are reachable from S, call it A star. All those nodes which are not reachable from S, I want to call it B star. So clearly S is reachable from S, therefore S is in A star. T is not reachable from S in GF because it stopped, the algorithm stopped. Therefore T is in B star, therefore A star B star is a cut, right. It's a cut because S is in it in A star and T is in B star, so it's a cut. So I made a cut, okay, I made a cut. Now I am asking a question, what property does this cut have? Is there any interesting property that this cut has? The answer is it does have interesting property. What is interesting property? If I take any edge UV which is crossing this cut boundary, then the capacity of this edge, if you look at this, called CE, then the flow on this edge must be equal to C, which means this edge will be saturated. Okay. Is there a question? No. Okay. Any edge which is crossing the boundary of this cut, which cut? The cut I have constructed by looking at all the nodes which are reachable from S in A star, nodes not reachable from S is in B star. So therefore, if there is a forward edge like this in the graph, right, from U to V, then the flow must saturate this edge. Why? Because if it is not saturating this edge, then there is a balanced residual capacity on this edge called CE minus FE, which is greater than 0. That balanced capacity will result in having an edge in the residual graph GF. If there was an edge in the residual graph GF, then U is reachable from S, which we know because U belongs to A star. V is connected to U via a path, via an edge which has an edge which is positive weight. Therefore, in GF there must be a path to V. So then V would not have been in B star, V would have been in A star. So the only way that V can be in B star is that this edge is saturated. Is that clear? That's the only way that V will be in B star. V is not in A star, which means V is not reachable from S. Only way that can happen is that this edge is saturated. So every forward edge is saturated. Similarly, if there is a backward edge from V prime to U prime, I am claiming that this edge basically has 0 capacity. Why is that? It has 0 capacity. Not 0, its flow is 0, okay, which means that the weight of it in the residual graph is 0, which is not there in the residual graph. Why is that? Because if the flow does not assign a 0 value to this edge, then there will be a dotted undo edge that I will have from U to V, U prime to V prime. If this flow Fe prime were non-zero, if it were greater than 0, then I would have put an undo edge from U prime to V prime. And because of that undo edge, the dotted edge from U prime to V prime, there will be a path from S to U prime to V prime, but we said that V prime is in B star, which means there is no path. So the only way that V prime will be in B star and not in A star is if this backward edge, this V prime U prime edge, right, which is going from B star to A star, is empty. It's not carrying any flow, right? Fe prime is 0. So the interesting property we have in this cut is that edges out of A are fully saturated and edges into A star are empty, are unused. This is a property we have. And because we have this property, therefore if I do the arithmetic, value of the flow Vf is equal to F out A star minus F in A star. F out A star is equal to Ce, sum of Ce out of A star, because every edge out of A star is saturated. Therefore, F out A star is simply the sum of all the capacities of the edges out of A star. And F in A star is 0 because every edge which is pointing inward is unused, is not used, is empty. Therefore, it is 0. Therefore, the sum of all the capacities going out of A star is simply the capacity of the cut C A star B star. Okay. Now, clearly this is the first time you may be seeing this. If so, then you might find this going too fast. If you stare at it 2-3 times, you will understand it. Okay, if you stare at it 3-4 times, you look at this proof, you will understand it. It's very simple actually, the proof. It says therefore that the cut capacity and the flow capacity. The flow that I get at the end of 4 Fulkerson is exactly equal to the capacity of the cut that I got, A star B star cut that I got. Therefore, A star B star must also be the minimum cut, because no flow can have a capacity which is more than the minimum cut. And I found a flow which has a capacity of a cut, right? All the flows will have a capacity which the flow value will be less than all the cuts. So I found a flow which is equal to a cut, which means this must be the minimum cut. So I found a minimum cut also. Okay. So 4 Fulkerson finds for me a minimum cut. How do I find this cut? Take all those nodes which are reachable from S in the residual graph, and that is called A star. Those that are not reachable is called B star. That's the cut. I'm done. Okay, so now remember we discussed in the first class, we discussed this thing called bipartite graph. We talked about bipartite graph. We said, can we find out if a graph is bipartite? How do you find out if a graph is bipartite? We said use the breadth first search. It will find out whether the graph is bipartite. Graph is bipartite basically if you can divide the graph into 2 sets of vertices, V1 and V2. Edges lie only between V1 and V2. So you can imagine V1 is basically students, V2 is basically employers in their placement season. All students want the best jobs, right? All the jobs want the best students. But clearly, finally in the end, students might end up getting jobs which are not the ones that are the best, and the companies might end up getting students who are not necessarily the best, isn't it? So if you sort it in some sense, you will find that over here, these are the best jobs and the best students. You get a lot of edges here, very few edges going like this, very few edges going like that, but eventually you will find for every student you will be matched to one job, and when that student is matched to a job, you get what is called a matching. So these colored lines which I have shown here is called a matching. Matching, what is a matching? Matching is assigning to every student a job. That's called a matching. These could be men, this could be women, and you could be trying to arrange your matrimony site, right? bharatmatrimony.com. You could be trying to arrange marriage between man and woman like this. That's another problem. Okay. So any of these kinds of problems where you're trying to match courses, students to courses in the institute. Student wants to do elective, professor wants to take students and so on. So professor wants the best students, students want the best elective, and you have other students and electives and so on, so you have to do, right, matching. So an association of students to electives is called a matching. So something is called a matching if it is incident on exactly one vertex in V1 and one vertex in V2. Then it's called a matching, which means that a matching, this colored edge, if you look at, it has the property, right, that you don't have two colored edges connecting a vertex in V1, and you don't have two colored edges connecting a vertex in V2. So, and if you look at the edges, once I have put an edge to a vertex here, this vertex has to be removed from the matching. It can't be used again. Okay. So every vertex in V1 is incident on at most one edge. of the matching. Similarly, every vertex of V2 is incident on at most one edge of the matching. If it is exactly one edge, then it's called a perfect matching. It means that all the vertices are covered. So this colored thing which I have shown you is a matching, but it's not perfect because this particular vertex is left out. Imagine you are trying to create a situation where you are giving every student, trying to give every student a job. Some jobs don't have students and some students don't have jobs. Okay, I have left out one student and I left out one job. This is not a very good idea, right? Because you know basically the number of students and jobs are exactly equal. I should have tried to find a matching in which every student got a job and every job got a student. But here I have found a matching, but it's not perfect. One student didn't get a job, one job didn't get a student. So matching is called perfect if every vertex over here is connected by an edge and every vertex over here is connected by an edge. It's called perfect. You may not have a perfect matching, okay? So, but if there is a perfect matching, that perfect matching will also be a maximum matching. What is a maximum matching? A maximum matching is a matching which has the largest number of edges. So I am trying to do the best possible, trying to find the best possible match between the students and the jobs. That's called maximum matching. If it has a perfect matching, then the maximum matching will also be the perfect matching. Okay. Now there are algorithms for matching. I mean, you don't have to use flows, but the most elegant algorithm, very easy to reason, prove everything for matching is by using flows. How do I use flows to do matching? I add a source vertex S, I add a target vertex T, I connect S to all the X's, I connect T to all the Y's, right? Y is one side of the graph, X is the other side of the graph, and make all these edges directed like this. Okay, make all these edges directed like this. Now what capacity should I put on these edges if I want to find a matching? What capacity would I put? Is the question I am asking, okay? What capacity would I put? Now if I put the capacity of 1 on this edge, if I put a capacity of 1 on this edge, it means that a flow originating, if I am trying to maximize the flow, it will take a flow of 1 on this direction. Now this one direction, this flow which is going on this direction, it will come to x1 and it will go out. There is only one edge here, so it will go out on this edge. A flow coming in this direction has a value which is 1. Now it can either go like this or it can go like this. If it goes like this direction, you put a flow of 1, then the flow is used up, right? Because of conservation condition, this is 1, so used up. So therefore, in this direction I cannot put any flow. Okay, so by putting connecting all the X's with S and putting a capacity of 1, I am ensuring basically that only one out of these edges, if X4 has 2 edges going out, only one of the edges can be selected. X5 has 3 edges going out, because the capacity of this edge is 1, therefore that one can only go on one edge, right? Because the minimum flow I can put on an edge is an integer, so it's 1. I can only put 1. So therefore that 1 is either written here or here or here. If that is put on this, then you can't use these two. Therefore only one out of the edges will be chosen. Similarly, if I put a flow, if I put a capacity of 1 on these edges, then make sure that, like say Y3 has 3 edges coming in, since this outgoing edge has only capacity of 1, therefore only one of the 3 input edges can be chosen. Okay, so the definition of flow ensures that if I, as long as I put the capacity as 1 for all these edges and all these edges, only one edge for every vertex I can choose here and over here, and therefore I will definitely find a matching. If I find a maximum flow, that flow has to go across this boundary between X and Y, and so that will cross, and each crossing that it's doing is carrying a capacity, carrying a flow of only 1, right? Therefore the total flow that goes is, let's say the flow I found is 10, maximum flow I found is 10. Since each edge carries only 1 flow, therefore the number of edges that I must have found is 10. Therefore the size of the matching in terms of number of edges and the value of the flow are the same, and therefore the maximum flow must be equal to the maximum matching. Is that okay? So I have reduced the matching problem to a flow problem, and I have reduced the maximum matching to the maximum flow. So since I have reduced the maximum matching to the maximum flow, I can simply use Ford-Fulkerson algorithm on this graph, and the result will be the maximum matching. Is that okay? So this is how you can take. I mean, this is a somewhat easier example to model as flow, but even somewhat looking problems that look very complicated, as long as some notion of capacity and use of capacity and all is going on, you should be able to model it as a flow problem and be able to do it. Okay, I am going to give you yet another example of an application of matching of network flow, which is taken from e-commerce world, because nowadays e-commerce is very hot and so on, right? And I am going to take a problem from the e-commerce world where you can use network flow, for which we need to do a little bit of work on the flow, okay, and convert it into what is called a circulation. So I am going to do a slight modification of flow called circulation before I can discuss this particular application. What is a circulation? A circulation is a flow, right, in which, you know, in a typical flow, when you find a flow, you will find basically that the nodes incoming and outgoing total flow into a node and total flow out of a node must match exactly. But in a circulation we don't demand that. We say the only place in a flow where we said okay, we made an exception was the SNT. We said at the source node you can have positive outflow. At target node you can have positive inflow, right? Because source is generating and target sink is sinking. Whereas for all internal nodes we said that source and the incoming and outgoing should match. So in a circulation we say that we don't need to match it. There can be a difference between incoming and outgoing flow for a node. The difference between the incoming and outgoing flow must be equal to the demand for that node. If the outgoing is less than the incoming, it means that some of the incoming is getting lost in that node. Okay, it's being sunk in that node. That amount that is getting sunk in that node is called the demand for that node. So the node is demanding something, right? So there is some amount of material that is going to the node. Some of it it's consuming, it's eating it up, right? A company is getting some material, it's consuming some of the material, and the rest of the material is selling in the market. So incoming material, consumed material, which is called the demand at that node, and then the balance material sent out. So every node has a value which is called demand, which is dV, and a circulation basically is defined as a flow in some sense, function f, such that Fe is less than or equal to C, so it should be less than the capacity for the edge. The F in minus F out need not be 0 as it is for flows, but must be equal to dV. That dV is the demand for the vertex. Okay. Now dV can be negative. If dV is negative, it basically means that node is a source, and dV is positive means that node is a sink. Okay, that's what it means. So we are asking the question: given a directed graph with demands on nodes, does it have a feasible circulation? Here is an example of a graph where I have written demands. So these are two nodes which have demands of -3, which means they are sources. They both generate 3 units. These are two nodes which have demands which are positive, which means that they are sinks. They want something. Okay, they are asking for. This guy wants 2. This guy wants 4. This guy doesn't want. He doesn't want anything. He's actually willing to give 3. This guy is willing to give 3. Okay, and then these are the capacitor edges. So this fellow is willing to give 3. This 3 can travel like this or it can travel like this. Okay, but if it travels like this, then since this guy can consume 2, the remaining 1 has to go somewhere. It can go like this. Okay, like that. So this is how you look at circulation. So remember that in this circulation you don't need sources and sinks, because everything is a source or a sink. Every node is a source or a sink in a circulation. Okay, so you don't need an additional source or sink node in a circulation. Now the circulation problem is not different from the flow problem, because we can just convert it into a flow problem. How do you convert it into a flow problem? Note basically that the total flow originating over here is 6. The total amount that is sinking here is 6. So there is a source of 6, there is a sink of 6, and I have a way of making it go from here to here. I have shown you how to make it go from here to here. So I will take 2 like this and 1 like this. I will take 2 like this, 2 like this, and you can see that this is a feasible circulation. Okay. Now this problem is not different from network flow, because what I can do is I can add a source node and a target node S and T to this graph, and if I want to make this a network flow problem, these internal nodes should not be sourcing or sinking anything, only S should be sourcing and T should be sinking. So since this guy is sourcing 3, if I don't want to source anything here, I want this to become neutral. How do I do that? Easy way of doing that is saying, okay, don't source anything. If you, instead of you sourcing, I'll give you 3. From S you connect an edge like this and give it 3. Okay, you connect S to source nodes, connect these two source S to these two nodes, connect T to these two nodes, right, and you put capacity of 3 on these two. Now I can take out this minus 3 from here. I can take out this minus 3 because initially this node was generating 3, now the 3 is coming through this edge from S. This node was generating 3, but now this 3 is coming from S. Therefore, I can remove this 3. Similarly, this guy was sinking 2, but now this 2 is going towards T. This guy was sinking 4, but now this 4 is going towards T. Therefore, I can remove this 4, 2, minus 3, and this problem just becomes a standard network flow problem. Okay, so I can convert every circulation into a network flow problem by just adding S and T and putting those edges with those capacities from S and T. And now I can run 4 Fulkerson algorithms and find a circulation. Okay, I can find a circulation. Slightly more complex variation of this circulation problem is one in which I might want to find a circulation which guarantees for each edge a minimum flow LE. Let's say I want to guarantee that I want to find a circulation where I don't want to put on it. So let's say on this edge I want to put a minimum value which is 1. On this edge I want to put a minimum value which is 2. This one minimum 1, this one minimum 1, this one minimum 0. So I am specifying the minimum value of the flow I want on each of the edges. I am asking a question, is there a circulation in which the minimum value is given as given here is like that. Obviously what I can do is I can start 4 Fulkerson with this flow. Whatever flow is written here I can start with that and I can do 4 Fulkerson and that should give me the answer. Okay. So the way of doing that, if I want to do that, basically way of doing that is that instead of minus 3, since I have a minimum value of 1 here and a minimum value of 2 here, right, therefore okay, right, so I can recompute the source and sink values based on this. Okay, so this guy is sourcing 3, this guy is sourcing 3, but you want to send out 3. Actually I should not have put minus 4, this should have been minus 3. Okay, anyway, so you can recompute the source and sink values based on the minimum values that I have written there, and once you have done that, then you can basically convert this again into a flow graph and then do 4 Fulkerson on it. Okay, so it's called the survey problem. Now every company that is selling products to customers wants to find out whether the customers like the product or not, right, they're happy with the product or not. So every company that is selling products wants to send out a survey to the customers such that they can get feedback. Now you want to survey the customers in such a way that if the customer has bought a product only, you will ask him questions about the product. It doesn't make sense to ask him questions if he has not bought the product. You will ask question to the customer only if, but if you ask too many questions, if one customer has bought 40 products and you ask him 40 questions, he gets fed up. So you don't want to ask him to rate 40 products. Right, Amazon for example, if you buy a product, it will ask you to rate. If you ask it to rate every product, if you ask you to rate, you will get fed up. So you should only ask him few products, you should ask him to rate. So for every customer, you want to give him only some products to rate. But you want to do it in such a way that for every product you can collect enough ratings. Right? For every product you must be able to collect enough ratings. So you want to give every customer only those products that he has bought to rate. You don't want to give him too many products to rate, but still you must be able to collect for every product enough ratings. This problem is called the survey problem. Okay. Now how do you model this survey problem? Very easy, alright, very easy to do it with network flow. Create a node called S. For every product, every customer you write a node called I, every product you write a node called J, create a node called T and create this circulation, right, this nice cycle like this called circulation. If I bought J, then you put an arc from I to J. If I did not buy J, don't put any arc from I to J. You will get kind of a bipartite graph. Customers are sitting here, products are sitting here, edges go from I to j if I has bought j. What capacity you will write over here? C prime I, which is the number of maximum number of products that you will give to a customer to rate is C prime I. You don't want to give him too many products to rate, but you will give him a minimum amount Ci. It can be zeros, okay? You want to give him a minimum amount Ci. You want, if you are going to survey a customer, you might as well ask him some products. So you will give him some minimum number of products Ci, but you don't want to give him more than C prime I. Similarly, for every product, you want to get a minimum number of responses Pj, right? And P prime j is the maximum number of responses, right? Which can be very high. You set it initially very high. You can set it equal to the number of customers that who have bought the product you want. Okay, but Pj is the minimum number of responses that you want to get. So you are saying basically that the capacity of this node is C, this edge is C prime I, this one is P prime j, but you want to set a minimum value of Pj and Ci. And now you can convert this. So this is a circulation problem, right? This is a circulation problem. So you can convert this into and 0 comma 1 over here, because this can be maximum 1, minimum 0. So you basically get this to become like what we did earlier. It's a circulation problem in which there is a minimum value for all the edge weights, and you can convert this into a maximum flow problem, and you can solve this using network flow. Okay. Unfortunately, we don't have enough time to try an example like this. If you had more time, we could try it, but you could try it yourself. I mean, you can try 3 products and 3 customers and then try to do it yourself. So there are very many interesting real life applications that you can put network flow. That's what I wanted to show you. Okay. So with that, I will stop. I mean, I'll just maybe just show you the result of that thing which I said I'll skip in the middle. I'll just show you that, and then we can take questions and discuss the answers to the problems that we did in the last class. So I hope many of you had a chance to actually work on the problem. I know many of you are doing many courses, so you're all busy, but if you don't try out these problems yourself, especially try to program it yourself, you are never going to learn anything. Okay. So I just want to show you this particular result. Okay. What this result says is that I can reduce the number of steps in the Ford-Fulkerson algorithm from order of m multiplied by c, right? Earlier it was order m multiplied by c. I can reduce it from order m multiplied by c to order of m square multiplied by log c. Okay, I can reduce it from order m multiplied by c to order m square multiplied by log c. Remember, c can be very large, so capacity can be like 1 million or something. So then log c becomes small, and m square might still be a small number, right? You might have 100 edges. You have 10,000 multiplied by log c, which is going to be much smaller than 1 million multiplied by 1000 or something, right? 100 or something edges. So m square log c might be much smaller than m times c, and so you can reduce it to m square log c. All you need to do basically is, and you can read these slides yourself and look at the proof, right? It's not a very difficult proof. All you need to do is, each time when you augment the capacity, don't augment the capacity by 1, but augment the capacity by some number which is large, 2 to the k. So take a number 2 to the k for some value of k and try to see whether you can find a path which augments the capacity by 2 to the k. If I can't augment the capacity by 2 to the k, then I reduce k by 1 and try to do 2 to the k minus 1, half. If I can't do 2 to the k minus 1, I reduce k by further 1, try 2 to the k minus 2. Like this, I keep trying to reduce the capacity starting from some large number. So if I'm initially I have paths, if I have a graph with capacity edges with capacity 100, for example, I could start at 2 to the 6, 64. I could try to find a path with weight with edge with a bottleneck of 64. So I can. In this case, I can find. And in case I can't find path with 64, then I reduce to 32, then I do 16, then I do 8, then I do 4, like that I keep reducing. And you can see such an algorithm will terminate in number of steps which is log of c. Okay, but in each step you might do order m square operation, which you can see if you look at the slides. So you can do m square log. Okay, this is a way to improve the Ford-Fulkerson. Many ways to improve Ford-Fulkerson. Let's discuss one of them. Okay, so with that, let us go to question and answer. So if any of you have worked on the problem, right, that I gave you last time and you have an answer, feel free to present your answer, we can discuss it. So you remember the problem sheet I gave you, or if you have questions about this session or other sessions, you can ask those questions also, right. So we're going to use the next 15 minutes entirely to interact. In case you don't have any specific questions, then we'll work on the problem set and we'll look at it, okay. So you remember the problems that we discussed in the last class? I think cut vertex we discussed a lot. Strongly connected components. Did any of you find an answer to this? How do you find strongly connected components in a graph? The classic method of finding strongly connected components that's discussed in your textbook, if you look at any standard textbook, is you run DFS on a graph, directed graph, find out all the post values, then invert the edges of the graph, run DFS once again, but this time when you run DFS, you visit the nodes in the order of decreasing value of finishing post times, and that will allow you to print the strongly connected component. This is standard algorithm that you might have seen in your textbook, but it's a little complicated algorithm because you have to run the DFS on the graph, then you have to invert the edges, find the transpose of the graph, invert the edges, try again and all. A much simpler algorithm is possible. Okay, much simpler algorithm is possible. Any of you have discovered any simpler algorithms? Did any of you look at these problems? So I sent out a bunch of hints yesterday, and maybe the hints got circulated to you by your teacher when it was optional. If you thought it was required, then it could have been circulated. So the hint tells you the answer. But anyway, any of you tried working this out? So you can come online through the interaction. You can chat, write your answer. How do you find strongly connected components using DFS? It's a question. Now, when we did the clusters in undirected graphs, I told you basically that you just maintain low counters. Low counter is the lowest pre-value encountered in DFS, and nodes which have low value which is equal to pre-value must be the root of the cluster. In fact, all the nodes which have low value, the same low value, they all belong to the same cluster. That's what I told you. But here we have a directed graph, and when you have directed graphs, that algorithm won't work. And the reason it won't work basically is because if you take this edge, this is called a cross edge. This cross edge creates problems for us. Why does it create problems? Because if you look at the low value, so when you did 9 you get 0, you get to 6 you get 1, 7 you get 1, right? So 7 can go down and it can see 6. So all of these nodes basically have the same low value as that of 6, which is 1. So 6, 7, 5, 4, 8 will all have one low value. Now since 10 can see 7, therefore 10 also will start seeing a low value of 1. So you will find basically 10 has a low value of 1, 9 has a low value, right, which is 0, and 10 has a low value which is 1, and you have this complicated thing, right, which is going on here. Because 10 can see 0, therefore 10 is also got a low value of 0. In this case it works. But what happens basically is because of these cross edges, the low values over here can get confused by these cross edges. But the good news about these cross edges is these cross edges are always pointing in the DFS leftward. Leftward means assume that the nodes on the left are things which you visit in the DFS earlier, and the nodes on the right are the ones you visit later in the DFS. So the cross edge will always be leftward. You'll never get a cross edge like this, because if you had a cross edge like this, then this node would have been visited in the DFS itself. So you'll always find cross edge like this. Because the cross edge is pointing leftward, what it means is that by the time you come to 10, you would have finished 7. You would have done 6, 7, 5, 4, 8, gone down like this, come out of 6. You would have finished 7. So 7's post value will be less than 10's current counter value. When you are in 10, you have current count value. The current count value will be less than 7's post value because you finished 7. And whenever you find that you have a current count value which is greater than the post value of somebody whom you are seeing through a dotted edge, it means that you have a left cross edge. That's the definition of left cross edge. When you have a left cross edge, basically you know that it's a left cross edge, you can ignore this left cross edge. Don't propagate low value. So if you don't propagate low value along cross edges, then you can use the same algorithm that we discussed last time, which means take all the nodes whose low value is equal to pre-value, they form the roots of the cluster. Those nodes which share the same low value, those nodes all belong to the same cluster, that algorithm will work. Okay. So that's how you do this problem, alright. Now this one I won't do here because it takes too long, and I don't think we will do both of these problems because they are proof and answer problem. Okay, let's take currency trading problem. This looks like an interesting problem, right? Currency trading. Any of you thought about the solution to this? Currency trading? I had sent some hint also. What does it resemble? Currency trading problem. What are we asking? We are saying basically that I have a bunch of currencies, rupee, dollar, euro, yen and all. I can convert one currency to another. This currency can be further converted. I can keep converting, right? As I convert the currency, of course I am getting a new currency. But if I come back to the same node again, then I have gone round, converted through several currencies and come back to the same currency. So I started with rupee, went around and came back to rupee. Normally, if I go into the market and do this, because every time I convert money into another currency, the fellow who is converting for me, he will make money, right? He will make exchange. He is not going to do business. He will keep some money and he will give me the rest. So I will find that if I convert to dollar and convert back to rupee, 100 rupees I convert dollar, and I convert back to rupees, I will get only 90 rupees. 10 rupees is vanished. That's what I find normally, right? Alright, excellent. So, yes, GEC. Can we get them up on the screen?
Sir, what I found is that the problem is similar to finding negative cycles. What you are doing is here except in the case of finding negative circles, we are doing addition and subtraction. Here we have to do multiplication and division and just see whether at the end of a particular cycle the value is positive. In the other case, we saw whether the value.
There you are checking whether the value is negative. In normal negative cycles,
here we have to.
Here you will check.
Yeah.
What you will check?
Here we have to check whether the value is greater than 1.
1, exactly. Excellent, excellent.
So from what I think, we can use Bellman-Ford algorithm to do the same.
Very good, very good. See, the negative cycle has the property that if I go around the cycle, the weight becomes negative. So if I go around it 2 times, it becomes more negative. I can keep reducing. Same way, if I go around a cycle which has total product which is greater than 1, I go around it, I get some gain. I go around it, I get another more gain. I can keep going around it, I can keep getting more and more gain. So therefore, the negative cycle problem and this multiplication problem are very similar, except as he rightly pointed out, instead of using addition and subtraction, they are using multiplication and division. Instead of checking for whether it is negative or 0, they are checking whether it is greater than 1 or is less than 1. Okay, so we should be able to use Bellman-Ford. Any thoughts on how you will write Bellman-Ford for this algorithm? If you remember Bellman-Ford basically kept in the bottom up Bellman-Ford algorithm, we kept an optimum value O, T, comma K. The optimum value from the source S to the target node T using edges no more than K edges, OTK. And you found OTK by, how did we do it? We said either OTK is the same as OTK minus 1, which means with K minus 1 edges I already found the optimum. Either this is the case. So you say M is equal to OTK minus 1. Either I found the value of the optimum already, or if I have not found the optimum, then I can improve the optimum by using an additional edge, which means now I will say M is equal to minimum of M, which is the value I found by using K minus 1 edges, and the value of O to some other node V with K minus 1 edges, right? And in the case of Bellman-Ford, we did plus the weight of the edge from V to T. Okay. So I took take a path of length K, which is consisting of a path of length K minus 1 plus this edge dt. and find the minimum of these and compare it with the minimum you already found, and that basically will give you, this is how Bellman-Ford was done. So in order to do this problem, firstly we are not finding minimum, we are trying to find opportunity. Opportunity for us is maximum. We are finding the value of a cycle. The larger the value of the cycle as a fraction, the more exchange gain we are getting, alright. So we are finding not minimum, so we have to change minimum to maximum, right. So if you can improve it, you are trying to improve it, in this case improving. Basically all I am saying is that when dynamic programming problems have a very powerful problems, okay, algorithms, you can typically use dynamic programming in very wide variety of situations. So just because we wrote a graph, an algorithm with plus and min and so on, don't be caught with that, okay. You have to look at whether or not the shape or form of your problem looks very similar to the shape or form of another problem. As we saw here, the shape of this particular currency trading problem looks very similar to the Bellman-Ford problem. Only we have to change min to max and plus to star and all that, okay. So this is how you do your typical things, okay. So typically this is how you do, when you have a given problem, you quickly see whether or not it looks like means I can modify the problem by changing things, make it look like some other problem, and then you try to use that technique, okay. Okay, if there are none, then we have run out of time. Thank you.